Sweet. Hello and welcome, everybody. I'd like to introduce you to Hayden. Hayden is a geospatial data scientist, and he's going to be telling us a bit about how he works to address unknowns in the realm of costing for bioenergy production. That is a mouthful, Hayden.
Sorry.
Yeah. Yeah, so it's a really, really important problem because by addressing these costs, you can make bioenergy production a lot more feasible, and yeah, it's very cool. Captain Planet would be proud. I think that's it from me. Are you ready for action, Hayden?
Yeah, happy.
Oh,
Cool.
actually, one more thing before we get started. I just want to remind everybody about the question asking mechanism. So if you type in, so go to the Slack channel for this talk, and then you can type in your question with a exclamation mark question in the front, and then your question will be able to pop up over here. So yeah, like if you have questions at any point in time, please ask them on Discord. They'll get added to a queue, and we'll ask them at the end. Awesome. Now it's your turn, Hayden. Take it away.
Cool, thanks. Hi, everyone. So, right, bioenergy. So firstly, I think what is probably a good idea is to talk a little bit about who we are and what we do. So I'm part of an organization called SAON, the South African Environmental Observation Network. And basically what we are is we're a subsidiary of the National Research Foundation, and we're focused on looking at how long-term environmental change affects South Africa. So we're a whole bunch of ecologists and botanists and biodiversity people and climate change experts and all of that. And they're all working away very hard. Now, one of the things that arose out of that was a need for data scientists and developers, and that's where I come in. So I'm part of a group called the Alwazi Node within SAON, and we specialize in basically how to take good science and make it understandable for people and make it into systems that can be used. So one of the systems that I've been working on is the BioEnergy Atlas. So I hope you've all got coffee. I do. And let's get on to it. So what is bioenergy? So in South Africa, we've got this problem of South Africa mostly needs coal. We've got a little bit of nuclear and we've got renewables such as solar coming online. But the problem with those technologies is that they can't directly replace coal. The only ones that can replace the petrochemical industry is something that uses carbon. And the only renewable forms of carbon are the bioenergy products. So the Department of Science and Innovation, a couple of years ago, about 2015 or so, decided that what South Africa needed was a tool set and knowledge repository to allow people within the bioenergy space in South Africa to make good decisions. And they also thought that what might work quite nicely is for the bioenergy industry to maybe stimulate some sort of green job process or something similar to that. So that led to the creation of the BioEnergy Atlas for South Africa. So what the BioEnergy Atlas is it's basically a repository and searchable metadata catalog. And what it does is it provides spatial information and it provides information around conversion technologies for producing bioenergy. It showcases a couple of case studies as to where spatial information and conversion data and so on gets used to actually help people get a project offline. And then what we've got is a whole bunch of decision support tools and some tools for assisting with industry collaboration. And if you guys are interested, you can access it through that URL. And what's really nice about it is that we've got a policy of being open source and open data. So any data that we use is free and publicly available, and the tools and models that we build are available to the public. Because we're a very new organization, a lot of these things are not mature, but the principle's there, we're getting there. So what is the basic bioenergy value chain? And that's the thing that we're trying to model here. So you've got your feedstock, which might be plants, or it might be sewage, or it might be animal carcasses, or it might be all sorts of things. But basically, if it's got carbon in it, it can be used as a feedstock. And then you've got a process where you've got logistics. So you've got the harvesting processes, you've got the transportation networks, you've got a whole bunch of stuff that happens. And then you've got the conversion step where you're basically taking your feedstock and you're converting it into bioenergy, and then you get bioenergy out. So bioenergy, where was I? All right. So the thing with feedstocks in South Africa is that it's inherently a spatial problem. So the availability of feedstocks is typically driven by climatic gradients. So you've got, where there's a lot of rainfall happening on the eastern side of South Africa, you've got a lot of bioenergy of feedstock being available. And then as you move into the drier parts of South Africa, less and less feedstock becomes available. Yeah, I've already spoken about that. So what conversion technologies are, so there are multiple different types of conversion technology out there. There are conversion technologies for producing biodiesel and conversion technologies for producing oils, ethanol or electricity or charcoal or all sorts of stuff. So each conversion technology has got its own economy of scale. And what often happens is that you need large capital investments in order to develop these. You know, if you wanted to build a big plant, you need a lot of money. So before people are willing to invest in a large plant, what they need to do is test the plant for feasibility. And the way that they do that is they calculate a thing called a levelized cost. And essentially what happens is that in our modeling platform, what we want to do is take a technology and feedstock combination and see where they price competitive to existing fuel sources. Because essentially that's what we're trying to do, is we're trying to replace fossil fuels with renewable options. And I'm going to walk you guys through this and how we've tackled these problems. So if you simplify, why is this not? Okay, so the problem is, how do you develop these scenarios for feasible bioenergy production? If you abstract the problem to its most simplest form, there are two factors that you've got here. Because of the fact that there's economy of scale, large processing, let me start this properly. Small processing facilities, that don't have a high throughput of biomass tend to produce bioenergy at a high unit cost of production. But then as the facility gets larger and larger, the production cost tends to drop. However, on the other side of the coin, you've got costs of transport. So if you've got small facilities, you have got a low cost of transport because, if you only need 1 kilogram of biomass a year in order to keep your pizza oven going, you don't need to travel far in order to get it. However, if you've got a ginormous facility, you're going to have high transport costs because, you need to source the biomass from somewhere. So at some point in the middle here, you've got the unicorn zone where you've got a nice balance between your scale of facility and your unit cost of transport. And that's the point where you're going to have the lowest unit cost of manufacture for your bioenergy product. Now, this is a spatial problem because the availability of bioenergy varies in space and time in South Africa. So how do you model that? And where does the Python come in? So essentially what we've done is we've broken it down into a couple of components. The first component is, how do you get an idea of the costs of transporting biomass to roadside? So given that you know roughly where your biomass is, what are the costs of getting that thing to the nearest road? Because sometimes trees are growing on cliff faces, or it might be a distance that the farmer has to transport his biomass to a road, or so on. So we developed an algorithm called the virtual roads algorithm, which basically calculates the least cost transportation route from any point in the country to the nearest road. The next component is a thing called the location allocation algorithm, which says, okay, given that we know where in South Africa the biomass is, where are the optimal places for us to put bioenergy facilities? Then what we've got is the conversion model, which uses the information from the previous two models in order to calculate things such as capital expenditure, operational expenditure, emissions, a whole bunch of other parameters. And then what we do is we take those parameters and put them into a nexus model, which enables you to perform comparisons and select technologies based on feedstock and investment and requirements and so on. So why did we use Python? And mostly it was because there are such incredibly mature libraries out there for performing scientific programming tasks. The main ones that we used are scikit-learn, and then that was mostly for the raster processing side of things. Then we used NetworkX for doing graph traversing and shortest path calculations and so on. And then we use GDAL and OGR for dealing with a lot of the spatial information that we have. Good old pandas and geopandas for calculations, and then Dash, Plotly, and Matplotlib for data visualization. And then because we've got most of this information stored inside Postgres databases, we use PsychoPG for all of that work. So the virtual roads algorithm. What this map is it's a map of South Africa, and all of those pink lines represent the roads of South Africa that can be driven by a car. And as you can see, it's an enormous network. I think there were 48 million nodes inside this network. And basically what we need to now do is calculate, okay, how do you move off-road to that particular road? So I'm going to go walk you through this by going through an example data set and basically walk you through the process. So this is an aerial imagery of our target area of interest. And believe it or not, there are some roads there. You can see there's one over there, and there's another one which goes around there. And then we have a river that's going through it. And how do you calculate an off-road point to that road? So the first thing that we needed to do was take a look at the different forms of publicly available data sets that cover all of South Africa. And what we settled on using was a thing called the Shuttle Radar Tomography Mission, or SRTM, digital elevation model for South Africa. And that's what you've got there. And basically what that enables us to do is it enables us to generate a cost surface for the algorithm to move over. And the way that we did that is by first creating a slope raster. So we calculated, how steep the different slopes are within our target area. And then areas with a slope that exceeded a certain threshold were then excluded. And basically we set the cost of moving over those areas to infinity, so that the algorithm didn't try to go over mountains, because that's expensive. Then what we also did is we had a look at features such as rivers, military zones, conservation areas, and had a whole bunch of other parameters that we used to create exclusion zones, and that generated our cost surface. Then what we did is we burnt the roads into that final raster to say, okay, these are the roads that you need to navigate to. So after doing that, what we then did is we converted these things into points. So if you look at this map over here, we've got every green dot represents a potential start location for our algorithm. And the red lines, the red dots over there represent the destination points that we needed to navigate to. And essentially what we did here was a windowed approach, because what happens is that if you've got, if you work with tiles the way that geospatial people do previously, you don't know which are the, beyond this tile, what does the landscape look like? Typically, the algorithm doesn't know. So the way that we got around this was by selecting a start point, say it was that one over there, and then we calculated all of its nearest neighboring endpoints. And then for the next point in that, we then did the same thing. Where are all of your neighboring endpoints, closest neighboring endpoints, and so on. And so we went through that array, basically finding all of the neighboring endpoints. And then we merged all those arrays and basically selected a unique set to say, okay, these are all of the potential endpoints that are closest to our start points. And then what the algorithm did is it clipped out a large raster around that particular area in order to perform the traverse. And that's basically what you see over here, is that all of these least cost paths are then going to a road. And then what also happens is if there's an option of, say, this one, it's cheapest if I join up with my neighbor's path, then that also is what takes place. So you're not generating a million paths for each unique start point. They link up to each other. And then basically what happens is that this windowed approach moves through the entire array of start points and generates all of these least cost paths. So what does that look like as a decision model? It looks something like that. And in the name of time, I'm going to suggest that if you're really interested in it, you can have a look at our GitHub page, or you can go onto the BioEnergy model website and work through some worked examples. So essentially what that resulted in for South Africa is millions and millions and millions of little lines, each representing the least cost pathway to a road. And if you have a look at what that translates to for all of South Africa, it looks something like this. I tried drawing it using just my little laptop, and this is the point where it died. It could not hold any more of these things in its memory. And what's nice about taking this variable window approach that I described is that it means that the size of your windows varies based on the size of and the kind of dimensions of the network that you've got. So you can see in areas where there's a sparse network, you're typically processing much larger areas, but then in areas where there's a dense network, your tiles that you're processing get a lot smaller. So that was one of the ways that we optimized this type of analysis for the complexity of the data. So now you know the least cost path for moving biomass to roadside. Okay, cool. So now what we need to do is start working through this thing in order to perform a location allocation. So for that, we've got a whole bunch of different inputs. We've got our road network input, which is existing roads in South Africa. We've got the virtual roads input, and then we've got other inputs such as where are the feedstocks potentially located, and then we've got information around the different conversion technologies, and then we've got various user-defined parameters such as transportation parameters, and one of the ones we used for that is a thing called CPK, which is cost per kilometer. So that basically enabled us to assign a rand value for each of the biomass conversion facility catchments that we developed. And then what we went through is the biomass acquisition thread. And then from there, that locates the facilities, and then you can start calculating various derived parameters from there. So in terms of locating bioenergy conversion facilities, we actually took a similar approach to what we did with the virtual roads algorithm, where we said, okay, these are the point sources of biomass. And in this particular example, it's just being represented by these little columns. And essentially what the algorithm does is it performs a first pass and says, okay, for a facility of, requiring 30,000 tons of biomass per annum, where's the cheapest place for me to put that facility? So it'll look at all of the, it'll do like an area weighting basically, and it'll then say, okay, that's a location where the transportation costs are minimized and I can get my X number of tons of biomass per annum. And so that's the first iteration. And then what it does is it then goes through and repeats that process and says, okay, of the remaining biomass left in South Africa, where's the second best place for me to put my facility? And then it does a similar area weighting and puts it over there. And the main heavy lifter in this whole process was NetworkX, which is basically, we use Dijkstra's algorithm for traversing these networks. So the outputs from that were then used for aggregation, analysis, interpretation, and reporting. And the idea was to try and make these things available for Nexus type comparisons. Where are the best places, and what are the best combinations of feedstock and technology option for us to use for bioenergy production. So from there, okay, wait, this is just a pretty picture showing what the outputs look like. So the star represents the optimal location for you to put a facility. The yellow points represent roadside depots, and the green blobs represent the potential feedstock, and the blue lines represent routes that we can use for transporting. So this is an example of a static output, similar to what we produced for the different bioenergy options. So this particular conversion technology was ethligno, so it's producing ethanol from lignocellulose sources. The feedstock is bagasse, which is the leftovers from sugarcane. And you can see that, we modeled 28 facilities in South Africa with 19 on site, and produced some stuff. But what's maybe better to show off is what the live data looks like. So somewhere around here, I have a screen full of stuff. No, that's Hugging Face, which is very cool. Okay. So inside our BioEnergy Atlas website, we produced all of these static outputs, and we just embedded them as images for now. So you can then go here and you can see, okay, what is bagasse to ethanol? What do the different model outputs look like? What do the cost summaries look like? What does transportation look like? And so on, for all of these millions and millions and millions of different conversion technologies. And then from there, what we wanted to try and do was develop essentially dashboards that allow people to perform Nexus type calculations. So what I had wanted to show you guys was a fancy thing that I've been building using Plotly and Dash. But I'm really not happy with the way that Plotly and Dash are handling large geospatial data sets. So we've been looking at things like GeoViews and Datashader as better ways of presenting large geospatial data sets online, but it's not mature enough for me to show off. So what I'm going to show you is the ugly dashboard, which is this. And basically what you can do with this sort of thing is perform Nexus comparisons. So here you can see, okay, you've got the number of bioenergy options per region, and you've got the number that don't require additional subsidy, meaning they're cost competitive. So out of all of the options that we had a look at, they've 397 sites where you can potentially site a bioenergy refinery and actually make some money. Gives you some stuff around feedstocks, number of jobs you can produce, power generation potential, and then over here on the right, it gives you some information around, which are the ones that require additional subsidy of how much and which one, the technology options that work. And then over here, we've built filters. So you can say, okay, I'm only interested in the Eastern Cape. What does that look like? And everything inside here is dynamic. So yeah, that's what we've been working on with the BioEnergy Atlas. Kind of next steps, I think, are to start actually engaging with our broader stakeholder community to actually make this sort of stuff applicable. One of the biggest hassles that we've had is that our clients essentially don't talk spatial data, and they don't know how to use stuff that we produce. And so now what we need to do is start engaging with people and making this sort of thing more known and more accessible. So yeah, if anyone has any questions or would like to contact me, I'm available there.
Thank you, Hayden. That was awesome. There are about 1 million questions for you, so it looks like people are super interested in this stuff. Let me find the first one. Yeah. Okay. So, Leyland asks, out of curiosity, why would investors invest in bioenergy over solar and hydro?
So, it's complicated. So if you look at it depends on the investor, I guess. If you're an organization like Sasol, then spending time and money on supporting the petrochemical industry with a renewable alternative makes sense. People still need grease, you need oil in order to enable things to turn, that sort of space. So there's, regardless of what happens with electric cars or electrified grids, you still need hydrocarbons in order to enable things to move and to work. So I think that's the main reason why someone would invest in the bioenergy industry. Personally, I think that that solar and hydro make a lot more sense. But there are still certain use applications for bioenergy in South Africa.
Okay, that's awesome.
I mean, an excellent example of bioenergy is actually a braai. That's.
Sweet. Paul asks, with respect to virtual roads algorithm, wouldn't you get away with using Google Maps API?
So we had a look at the Google Maps API, and one of the biggest problems with that is that they put limits onto the number of hits that you can use publicly. So we'd use up our allocation in about a day, and not even cover a tiny portion of the country. It's not great, and also Google falls apart if you're trying to navigate off road. It doesn't know that there is steep cliffs or deep rivers that you need to go around. So that's why we developed our own custom virtual road routing algorithm.
All right. Bruce asks, were rivers detected by image processing or taken from an existing database?
So we wanted to do it by image processing, but it actually turned out to be quite a thing. So we wound up using an existing database. Fortunately, at SAON, we've got a number of hydrologists, and they recently modeled the quaternary catchments for South Africa. And so we just used that because, they kind of the authoritative crowd with this. Whereas through image processing, it's really interesting because in the more arid parts of the country, it's hard for you to discern between rivers and roads because dry riverbeds look a lot like dirt roads. And actually, we recently sponsored a Zindi challenge to address particularly that. And we're really looking forward to getting the algorithm for that and making it publicly available because it's going to be really cool.
Yeah, it does sound like a very hard problem.
Yeah.
Let's see. All right, Toby asks, great talk so far. Are you aware of Python PyPSA? We use it to model large-scale investment options, solar, water, coal, nuclear, etc., within South African power pool, except for, right, this is a really long question. I ended up copy-pasting. Except for a better, it's not weird to buy it. Wow, it works great, has served us well. Out of interest, I don't know Nexus. If you know PyPSA, would PyPSA be able to fulfill the Nexus function?
Sure. So I don't know PyPSA. So one of the problems that we've faced is that we're government funded, and as a result, we have to go through government procurement processes whenever we want to buy anything, and it's infuriating. So often we have to develop our own stuff in-house, just because it's buying stuff is often out of the question because there are no local suppliers or something similar. Nexus is something that we've been developing ourselves for basically multi-criteria. It's a linear programming thing, and yeah, it's kind of the big challenge is being able to optimize based on different user-defined criteria. So you can say, okay, if I'm going for jobs, want to maximize jobs, then what else has to give, and that's what we're using. But I'm going to definitely check out PyPSA. Thank you.
Cool. Victoria asks, did you consider PG routing instead of NetworkX?
Yes, we did. And basically, the reason it was actually like a personal choice. So I spent a lot of time playing around with NetworkX, so I was already familiar with it, and I did not want to spend a huge amount of time going down the PG routing option. The PG routing looks like it's really cool, and what's nice is that it all just works in Postgres. So, yeah, could have been great, but I just didn't have time.
Okay. I have a follow-up question on one of the previous questions, actually, around just like in-house versus buying stuff and government procurement. Don't you think it would sometimes be cheaper to just buy the thing in terms of man hours? Because I mean, I'm sure you cost a bit per hour, and then you. Okay.
Yes. So,
all right, fair enough.
So it's like a labor of Sisyphus. You can push your boulder up the hill as much as you like, but if there's policy in Treasury that says must have local supplier, then it excludes the entire universe of amazing things that you can buy. That being said, it opens up an awesome business opportunity. If anyone feels like setting up a shell company to become my personal local supplier for things.
Hey, I'll talk to you later.
You didn't hear me say that.
It could be our little secret. Cool. Colette asks, what data sets did you use again?
Shoot, a lot. So the biggest one, it depends on which aspect of this you're talking about. So for the virtual road stuff, in order to generate the cost surfaces, we used the SRTM data set, so the Shuttle Radar Tomography Mission, just because that's the highest resolution elevation model we can get for South Africa. And then what we did is we used the South African Surveyor General in order to provide us with the roads and what the different classes of roads were. We used the Department of Environmental Affairs data in order to get where all the conservation areas and protected areas were. because we don't want to be, driving trucks through there. We used what we know about the military bases in order to try and find out all of that. And then with regards to feedstocks, that's a whole other story. We spent most of the effort in this project has actually been developing spatial databases of bioenergy feedstock. So we've got sugarcane, we've got invasive alien plant species, we've got forestry residue, we've got used cooking oil, we've got sewage, we have abattoirs. It's just like finding out where all of these things are and how much they produce over time has been a big hairy deal. And a lot of it is also available. Agricultural residue is another one. A lot of it varies, its availability varies in space as well as time. So, some of it's only available during certain seasons. So it's hard to abstract that sort of stuff so that you can put it into a model. That was really interesting for me.
I snuck a question of my own in there. Sheena asks, how might adoption of biofuel have a negative impact? For example, could it harm biodiversity? So like if sugarcane production became ridiculously profitable all of a sudden, like would there just be more of that, and could it harm things?
Yes, it absolutely could. One of the biggest ones was there are numerous examples of this in Indonesia, where people are using jatropha in order to produce oils. And essentially what they're doing there is they're cutting down rainforest in order to produce biodiesel, and it's horrifying. So yes, there's absolutely potential for this thing to negatively impact biodiversity. So the way that we got around this in our studies was to basically model through those exclusion zones. We excluded areas of high biodiversity potential. We didn't model anything where it's a case of, it actually, there's a bigger question here, Sheena, which is, can things like bioenergy negatively impact food security? And the answer is also yes, because, you can use, if people are using mealies in order to produce bioethanol, what are people going to eat?
Everyone's going to eat it. Yeah.
Yeah, exactly. So the way that we got around that is by basically just not modeling it and not presenting it. But it's a big important problem. And I think that as the industry matures, how to tackle those sorts of things need to be handled. And what's nice is that, we've got good working relationships with the Department of Environmental Affairs and other organizations that should in theory be watchdogs for this sort of thing. So we try to build that in through our stakeholder engagement.
Okay. Yeah, it sounds like a very hairy problem because it's almost like forbidden knowledge once you've discovered it. Let's see what else is going on in this chat. All right, here's one. So Fuad asks, awesome work with the off-road routing. How accurate is it with respect to avoiding river elevation? And are the data sets freely available?
Yes, the data is all freely available. Where's the URL? So actually, what's probably better for me to share quickly is this, because then you can find all the data, not just. I'll put it in the Discord.
Put it in the private chat. I can bring it up on the screen. If I can find the private chat button.
Where's this private chat? There it is. Haha.
Yeah.
Okay.
All right. Yes, I do. There is a slight process to this. There we go. That is the URL.
Sweet. So that's the place where you guys can go in order to search all of Seon's metadata. And there's a lot. It's basically as much spatial data for South Africa as we can harvest. Is sitting there. It's a bit of a mess, but we're working on developing an API that people can use to query it directly. And that's probably what I'll present at the next PyCon.
Okay.
But with regards to how accurate it is, it's as accurate as the underlying digital elevation model. So I think SRTM is about 10-meter vertical accuracy. So that's the accuracy of the virtual roads algorithm.
Let's see. There was another cool one. Do you consider, so Paul asks, do you consider also biodiesel option where the farmer's tractor uses the fuel generated in the region of production? So I guess
yeah. So so we didn't model that specifically. What we're trying to do is develop tools that enable people to model this stuff themselves. But it's absolutely an option. There are a whole bunch of conversion technologies for producing biodiesel. One of the simplest ones is actually just used cooking oil. Farmers wanted to, they could develop a relationship with local fast food places. And, I sell you X number of things of fresh oil, you give me your used cooking oil at a discount, then that's a model that works really well. And we actually have a case study on that on the BioEnergy Atlas website.
That's awesome. So Leyland asks, is there a time frame for how long biomass has to be traveling before being processed? If would it not be a relevant heuristic in the model? So I suppose, does the biomass go off and become unusable or anything like that?
So it depends on the feedstock. If you're transporting something that's very volatile, then yes. But if you're transporting something that's less volatile, then sometimes time is actually a better component. So for instance, if you're looking at something like forestry residue, what that stuff's got is it's got a very high moisture content in the biomass. And so what you ideally want to do is chop it down and leave it in the field for a few weeks to dry out before you transport it, because otherwise you're transporting water, which is heavy. So yeah, it's absolutely a point, and it's quite complicated to model that. So what we worked on was tons of dry biomass where possible.
Okay. Julian asks, what are the main feedstocks available by kilojoules? How is bagasse currently utilized? Is that how you say it?
Yes, bagasse.
All right.
Yeah.
Sweet.
So in terms of kilojoules, let me bring up my thing, because I have a thing. I built it. Wait. Okay,
Should I bring it up?
Yeah, if you wish to. That's the thing. So in terms of just, we look at it in terms of tons of feedstock per annum. So you need to look at the energy density of this stuff. So molasses has got quite a high component, as does woody biomass and alien invasive biomass. And then maize residue is the next one in terms of these. So yeah, sugar has huge potential in South Africa, particularly because the sugar industry is busy, going through some strife at present, as no one uses sugar because it's bad for you. So yeah, so the sugar industry definitely poses a big option. Bagasse, for those of you that don't know, what bagasse is it's the leftovers as a result of refining sugar. So after they chop down the sugarcane stalk and they squish all the juice out of it, what you're left with is the fibrous stalks of the sugarcane. And currently there is utilization in the country for bagasse. Some of the sugar mills actually use it for cogeneration. So they just burn the bagasse and use that energy for running boilers and moving machinery with steam and, all sorts of advanced technologies like that. But yeah, what we want to try and do is help the sugarcane industry transition away from these very inefficient processes to more efficient ones. And that will require changing the way mills currently operate, but it also requires changing the way farmers work, because currently the standard thing to do before you harvest your sugarcane is to set fire to it, which is not good for retaining biomass.
And you finished that question literally in the nick of time because we have 1 minute until the next session. Yeah, so
I'll carry on in the
good
Discord
work.
if anyone has
And
other
that was
questions.
that was like pretty much the last question. Yeah, so Hayden will be on Discord. Go say hi. He's a friendly chap. And the next talk is by Take-A-Lot. So they're doing something on retries and circuit breakers in in Take-A-Lot microservices. So please go enjoy that talk. And yeah, thanks for coming, everybody.
Thanks for listening to me all. It was really cool. Ciao.